This is the Levitating Balloons Lab with Group 7B. We start by knowing that all objects around us have charged particles that exert electric forces on other charged particles. Even neutral objects have charged particles. We just know that the net charge balances to zero. This lab challenged us to design an experiment that would allow us to determine the charges on two balloons. Using a string, two balloons, a wool sweater, and some of Newton's laws, we found that each balloon had a charge of approximately 1.5 times 10 to the negative 7th coulombs, meaning that 9.6 times 10 to the 11th electrons were transferred while charging the balloons. This was done by taking the charge of a balloon and dividing it by the charge of an electron, which is 1.6 times 10 to the negative 19th coulombs. As distance between two charges increases, the force decreases as an inverse relationship. This is why the force decreases as the distance between the two balloons increases. So our experimental design includes us attaching one balloon to a string connecting to the ceiling in order to avoid grounding while allowing movement. This is our free balloon. We held another balloon still by its base to avoid as much contact with the experimenter as possible. We used a wool sweater to charge both balloons in the same fashion, 5 rapid back and forth movements, and place them exactly 0.079 meters apart. This is the distance that allowed the net force to equal 0. When they were both charged, the balloons repelled each other. We collected data for the mass of the balloons and the angle created while they were repelled at the zero net force. In order to increase accuracy, we controlled the distance the balloons were placed apart, as well as the amount of times and method of charging. We assumed only gravitational tension and electrical forces were significant and that any of the small attractive electrical forces between charged and neutral objects could be disregarded in order to simplify calculations. Since the balloons were charged the same way, we assumed they would have equal charges. We used Newton's second law, F equals ma, while calculating the other forces, such as gravitational, acting on the balloon so that we could use the F-net equation to solve for the electrical forces between the balloons. And that equation specifically is displayed above, as it is crucial to concept in the experiment. As you can see, electric force is inversely proportional to the distance squared between the charges, so it has to be constant in our experiment to determine the balloon's charges. We created our system schema to represent the experiment after the balloons had been charged and were interacting with each other. Thus, we did not include the sweater in the system. We included the hand and the string because the charged balloons would exert slight attractive forces to those neutral objects, but we assumed them to be negligible during our calculations. We didn't specifically label a contact force between Q2 and the string, as tension is a form of contact force. Our force diagram was key in calculating the charges of the balloons and can be seen on the slide. Ignoring the forces we previously discussed that were assumed to be negligible, we see the forces of tension, gravity, and each charge on the force diagram. Using Newton's third law of equal and opposite forces, we know that the electric force exerted by one balloon will be equal in magnitude but opposite direction of the force exerted on the other balloon. We assume that the charge of both balloons would be the same because they both began as neutral and were charged in identical fashions. Additionally, they both repelled each other, so the sign of the charges are identical. We believe our model is accurate because we controlled for all the variables aside from what we are testing for, and the value of the number of electrons transferred makes sense considering how small and abundant electrons are in the universe. This slide shows our results with the mathematical calculations of using our force diagram. We know that mg times the sine of theta would be equal to the force of the electric force because they would both cancel out to equal 0. So doing that, we got the numbers that are shown on the slide. This experiment was performed in a room with many other charge experiments being conducted, so there was an increased amount of charged particles in the room that could influence our system in addition to charged particles that already naturally exist in the classroom. Additionally, other charged objects that naturally exist in the classroom could be existing forces on the balloons, influencing our system as well. Balloons tended to be attracted to experimenters after being charged, likely transferring some electrons in the process, and because of our experimental design, we had to hold one of the balloons. There were likely interactions between the person and the balloon that caused some error. Ideally, an experiment like this could be conducted with no outside influence to isolate interactions to only those being tested. Based on the technology available, we had no other way to determine how many electrons were transferred due to the small attractive forces being between the charged balloons and the neutral string and hand. So we assumed them to be negligible for our calculations. Technically, these interactions would influence the charge of the balloons, and so this could have been a source of error.